The history of the Earth begins long before its own formation. To understand the actual age of the planet, it is necessary to completely abandon the human scale and adopt a cosmic perspective. The universe had already existed for billions of years when the elements that would form the Earth began to organize, scattered in a vast cloud of dust and gas in interstellar space. About 4.5 billion years ago, one of these giant clouds underwent gravitational collapse. At the center of this collapse, pressure and temperature increased until the birth of the Sun. Around this young star, a disk of material began to slowly rotate, forming the setting where the planets would emerge. Within that protoplanetary disk, microscopic particles constantly collided. With each collision, fragments joined together, gradually growing. This process, called accretion, transformed cosmic dust into increasingly larger solid bodies, leading to the emergence of the rocky planets of the solar system, including Earth. Earth was born as an unstable protoplanet, subject to violent impacts and extreme temperatures. Its surface was completely molten, unable to support any form of life. This initial period was marked by frequent collisions that shaped both the size and the chemical composition of the planet. For millions of years, the Earth was struck by asteroids and comets in a phase known as the Late Heavy Bombardment. Each impact released enormous amounts of energy, keeping the surface in a liquid state and constantly redefining the structure of the newly formed planet. One of the most decisive events in Earth's history was the collision with a body the size of Mars. This gigantic impact ejected material that eventually coalesced to form the Moon. This event not only created the natural satellite, but also stabilized Earth's rotation axis. After the impact that created the Moon, the Earth began to cool, slowly. The gradual loss of heat allowed for the formation of a solid crust. This moment marked the beginning of the preservation of the first physical records of the planet's history. Even with the crust forming, volcanic activity was intense. Volcanoes released large volumes of gases, contributing to the creation of the primitive atmosphere. This environment was toxic, hot, and completely different from the one we know today. The initial atmosphere of Earth was primarily composed of carbon dioxide, water vapor, methane, and ammonia. There was no free oxygen. Nevertheless, this atmosphere played an essential role in regulating temperature and protecting against solar radiation. As the planet continued to cool, the water vapor present in the atmosphere began to condense. Intense rains fell for millions of years, filling surface depressions and giving rise to the first oceans. The presence of liquid water so early in Earth's history is one of the most important discoveries of modern science. It indicates that the planet became habitable relatively quickly, creating favorable conditions for complex chemical processes. But how do scientists manage to determine the age of the Earth so precisely? The answer lies in radioactive decay. Certain chemical elements spontaneously transform into others over time, at extremely predictable rates. By analyzing the ratio between radioactive elements, such as uranium, and their decay products, such as lead, it is possible to calculate how much time has passed since a rock solidified. These processes act as natural clocks that measure billions of years. The oldest rocks found on Earth are about 4 billion years old. However, they do not represent the total age of the planet, as constant geological activity has destroyed much of the original crust. To go even further back in time, scientists analyze microscopic crystals called zircons. Some of them, found in Australia, indicate that the Earth already had a solid crust more than 4,400 million years ago. Lunar rocks provide independent evidence. They are virtually the same age as the oldest rocks on Earth, confirming that both bodies formed during the same period. Unlike the Moon, the Earth is geologically active. Tectonic plates continuously recycle the crust, erasing old records and creating new ones. This dynamics explains why traces from the planet's early days are so rare. This vast span of billions of years is known as deep time. It challenges human intuition and demands a new way of thinking about history, where seemingly slow events shape the planet irreversibly. The Earth we know today is the direct result of these initial processes. Every mountain, ocean, and continent bears marks of an extremely long and complex history. Understanding the origin and age of the Earth is the first step to understanding everything that came after. From that point, the planet was ready to begin the most extraordinary chapter of its history. With the Earth's crust stabilized, the Earth entered a phase of continuous transformation. The planet's internal heat drove the movement of tectonic plates, fragmenting and rearranging the surface over billions of years. This process created oceans, continents, mountain ranges, and deep trenches, establishing the geological rhythm that still shapes the planet. Over time, continents have united to form supercontinents and later fragmented again. These cycles have influenced global climate, ocean currents, and the distribution of minerals, leaving deep marks on the Earth's geological history. Volcanism played a central role in the evolution of the planet. Volcanoes released lava, gases, and minerals, constantly renewing the surface. At the same time, these processes enriched the primordial oceans with chemical elements essential for complex reactions. The Earth's atmosphere continued to change. Initially dominated by toxic gases, it underwent gradual changes as new compounds were released from the planet's interior, preparing the environment for even deeper future transformations. The first oceans were neither calm nor stable. They were subject to high temperatures, intense geological activity, and constant external impacts. Still, these environments became natural laboratories where the chemistry of life began to develop. In the depths of the oceans, hydrothermal vents released heat and minerals directly from the Earth's interior. These locations created energy-rich microenvironments, shielded from solar radiation, considered by many scientists as possible cradles of life. In these extreme environments, simple molecules began to organize into more complex structures. Amino acids, lipids, and other fundamental molecules emerged through natural processes, without the presence of living organisms. Over time, these molecules began to group together in systems bounded by primitive membranes. These systems, known as protocells, were not alive, but exhibited characteristics that preceded true life. The first forms of life emerged in a simple and microscopic way. These primitive organisms fed on chemical reactions available in the environment, starting the long biological history of Earth. The oldest evidence of life comes from structures called stromatolites. Formed by colonies of microorganisms, these fossil records indicate that life existed more than 3.5 billion years ago. Some of these microorganisms developed the ability to perform photosynthesis. By releasing oxygen as a byproduct, they initiated a radical transformation in the composition of the Earth's atmosphere. The gradual accumulation of oxygen led to the so-called Great Oxygenation Event. This process was devastating for many existing life forms, but paved the way for more complex organisms. The presence of oxygen altered the chemistry of the oceans and the atmosphere. Minerals oxidized, new biogeochemical cycles emerged, and the planet entered a new phase of environmental equilibrium. With higher levels of oxygen, multicellular organisms began to appear. Life ceased to be exclusively microscopic, increasing its diversity and complexity. The oceans have become increasingly complex ecosystems. Relationships between predators and prey have emerged, driving biological evolution at an accelerated pace. As life evolved, geology continued to record each stage. Layers of sediment slowly accumulated, preserving information about ancient environments and organisms. The Earth's climate has undergone extreme changes. Warm periods alternated with ice ages, directly influencing the evolution and distribution of life on the planet. Geology and biology have become inseparable. Life began to modify the planet, while the planet continued to shape life in a continuous cycle of mutual influence. The Earth has ceased to be just a rocky body. It has become a dynamic system, where physical, chemical, and biological processes operate in an integrated manner over deep time. At the end of this phase, the planet was radically transformed. Earth had become a living world, ready to receive the final chapters of its history, including the emergence of humanity. When we observe the complete history of the Earth, human presence emerges extremely late. After billions of years of geological and biological transformations, small groups of hominids began to walk through landscapes shaped by forces much older than any culture or civilization. The oldest known stone tools are only a few million years old. In geological terms, this represents an almost imperceptible moment. Nevertheless, these objects mark the beginning of humanity's ability to consciously modify the environment. The mastery of fire was a turning point. It allowed for cooking food, deterring predators, and inhabiting previously inhospitable regions. This cultural advancement occurred on a planet that had already accumulated billions of years of natural history. The rock paintings reveal more than just art. They demonstrate that humans were already seeking to understand the world around them, record experiences, and transmit knowledge, even without fully grasping the depth of geological time. Many ancient civilizations built monuments aligned with the sun, the moon, and the stars. These structures reflect the human attempt to organize time by observing natural cycles that have existed long before humanity. Primitive calendars emerged as tools to predict seasons and organize societies. Although limited, they represent an important step in humanity's attempt to measure and understand the passage of time. For centuries, it was believed that the Earth was young. This view began to change with the emergence of modern geology, when scientists started studying layers of rocks and noticing patterns inconsistent with a short history. The stratigraphy revealed that rocks accumulate slowly, layer by layer. Each stratum represents a distinct chapter, indicating that the Earth needed to be much older than previously thought. Fossils found in different layers showed a clear succession of life forms. This sequence reinforced the idea of a long history, marked by the emergence, transformation, and extinction of species. The definitive confirmation came with radiometric dating. Physics provided a quantitative basis for what geology had already suggested. The Earth is billions of years old. Archaeology, in turn, deals only with the final chapters of this story. Even the oldest human artifacts are extremely recent when compared to the age of the planet. In a short period of time, humans spread across almost all continents. This rapid expansion strongly contrasts with the slowness of the geological processes that shaped the Earth. The emergence of agriculture marked the beginning of more intense environmental changes. Forests were converted into fields, rivers were diverted, and ecosystems began to be transformed on an increasing scale. The first cities consolidated the human capacity to alter landscapes. However, these changes were still small in the face of the natural forces accumulated over deep time. With the Industrial Revolution, human impact accelerated in an unprecedented way. The extraction of resources and the release of pollutants began to influence entire planetary systems. The view of Earth from space revealed a finite, fragile, and interconnected planet. For the first time, humanity was able to see the result of billions of years of evolution in a single image. Today, human activity has become a geological force. Climate change, loss of biodiversity, and chemical changes in the oceans demonstrate the extent of this influence. When compared to deep time, human existence is extremely brief. Still, in just a few centuries, our species has altered processes that took millions of years to establish. The Earth will continue its trajectory regardless of humanity. However, understanding its age offers us a rare opportunity to act with awareness and responsibility. Knowing the age of the Earth is recognizing that we are part of a story much larger than ourselves. If this perspective has broadened your way of seeing the planet and the universe, follow us.